Good afternoon. It's really my pleasure to join you today at the Japanese Society of Ocular Circulation and the International Ocular Circulation Society meeting. And I'd like to thank Professor Ogura for inviting me to share with you our results, and also Novartis for supporting this symposium. Today, I'd like to tell you about what we've learned from analyzing choroidal neovascular membranes in 3 dimensions. And this is a powerful technology this is a powerful technique that's facilitated by OCTA angiography. So I have no relevant financial disclosures. And so our questions were, do we have any parameters on OCTA that allow us to predict treatment intensity and when patients are going to need treatment, just based on OCTA? And the second question we had was, were these lesion parameters in choroidal neovascularization somehow related to the choriocapillaris ischemia? And I'll walk you through our thought process and analysis here. So overall, when we look at OCTA angiography, we were all very excited to see the entire lesion with all its ramifications. And we thought that wouldn't it be nice if we had some parameters that we can look at from a OCTA, and it tells us how frequently we're going to need to treat this eye. So for example, a lesion like this, maybe the parameters we spit out from analyzing the lesion complexity would tell us, oh, this is an eye that only requires very frequent injection, maybe a monthly treatment regimen. And another lesion that looks somewhat like this, maybe the parameters that we obtain tell us that this is a quarterly extended treatment eye that we can start extending very rapidly. So that's really what we've all been thinking about. And one of the first papers that came out was from the French group by Eric Souillet. And in their hands, they were able to identify lesion parameters that correlate tightly with treatment decisions from OCT. So when they looked at the OCTA, they were able to see things like this, where there's peripheral loops. They call this a Caput-Medusy parameter or a feature. And these lesions required treatment every time they saw them. And when they saw these lacy wheel patterns, again, these eyes had all these arches and peripheral anastomosis, and they were confident in the treatment decision based on these parameters. Here's another feature that also correlates with treatment intensity, which is the CFAN pattern. And then correlate that or contrast that with this appearance of a dead tree with not many branches, not many anastomoses. And these are usually eyes with a scarred lesion that does not require treatment. So in our hands, when we got our OCTA, we started to see these lesions, and we wanted to extract these features that the Souillet group talked about. But unlike these very creative, positive features that they were able to extract, every time I looked at a lesion, I only saw very negative appearances. So it wasn't really going to work for us. So at the time, we had a very talented research fellow, Philip Roberts from Vienna, and we looked for maybe quantitative features that aren't as subjective and as creative, perhaps. And we found this NIH-free tool, angio tool, where you could extract your CNV, insert it in that tool. It's sort of a ImageJ type tool. And from that tool, you had a multitude of quantitative parameters: lesion area, vessel area, junction density, and lacunarity. And we thought maybe these quantitative features would be easier to extract, more objective, and perhaps correlate better with treatment intensity. So we had a cross-sectional study of all the patients that were in our practice at the time, and they had already achieved a treatment balance of treat and extend parameter interval. So we decided that anyone who was needing treatment more frequently than every 6 weeks was a high frequency injection eye, and anyone who we could extend beyond 6 weeks was perhaps a more desired treatment outcome, where these were low frequency injection eyes. And so we compared the qualitative features that were described by the Souillet group and also the quantitative features that we extracted from AngioTool. So here's an example. This is an unPAS OCTA. You extract the CNV and then you apply the AngioTool and extract all these features. So what did we find? So at the time, we had a very limited sample of 7 eyes in high frequency and 7 eyes in the low frequency treatment. And we looked at the qualitative features from the CED group. We did not find any difference between the two groups. And so we were optimistic about our quantitative analysis, but we still did not find any statistically significant differences between the two groups of high and low frequency treated eyes. And so to explain those results, we thought about the concept of angiogenesis in general. So you start with a normal eye where the vessels are very functional, branching in a normal fashion, and you increase the angiogenic signal, and then you get these abnormal dilated tortuous vessels with high anastomosis features, and that's basically the leaking CNV that we have. We start treatment with anti-angiogenesis, and somehow we achieve the balance. We rebalance the system with pro and anti-angiogenesis signals, and we get to a more normalized vasculature. And if we treat too much, we give too much anti-VEGF, we can destroy these remaining vessels and have a dysfunctional tissue. And in cancer, that could be undesirable because chemotherapeutics don't access the cancer and could grow relentlessly. So we hypothesized that in our eyes, regardless of the treatment frequency, we were achieving this normalized balanced anti and pro-angiogenic signal. And for the different eyes, regardless of the intensity, we achieved this balance, and therefore we could not find a difference in our vascular parameters. But another feature we were ignoring about the CNV is the complexity in 3 dimensions. So we're taking these complex features and collapsing them in 2D so we can analyze them with the AngioTool. So here we had a MD PhD student, Brian Satikno, who helped us adapt the projection removal software that developed by Yali and David. And here it's really the annoying feature of projection artifacts, especially at the level of the RPE. So if you take a slab of OCTA at the level of the RPE, you'll see projected on it all the retinal vessels. And that can be very undesirable when you're trying to analyze a CNV that grows underneath the RPE. So once we applied that software, we were able to see that it removed these projection artifacts. Here's an example of a projection artifact at the level of the RPE, and with projection removal, we then were able to get rid of these undesirable artifacts. And from measurements, this allows us to objectively quantify the thickness of the CNV. And lo and behold, once we applied this software, we were able to see that there are CNV lesions that have more than one layer. And that's sort of like the London double-decker bus. So we have lesions that are a lot more complex than we first thought. So from these analyses, we were able to extract a few quantitative features. So first, we had the CNV flow signal height. So here we took the Brooks membrane as the baseline, and we saw the distance between the Brooks membrane and the highest flow signal. We measured that, and then we looked at the number of CNV flow layers. So here, above the Brooks membrane, there's one layer, and then there's another layer just below the RPE. So this is a double-decker CNV. When we looked at the demographics of these eyes, so now we had a larger sample of about 50 eyes. The main difference wasn't the duration or any of the demographic features, but the frequency of injections and the interval between these injections. So the high frequency had more frequent injections and smaller interval between the injections. So when we looked at the 3-dimensional features, we found that they were significantly different between the two groups. So the more complex, higher flow signal, more number of CNV lesions were eyes that required more frequent injections. The other feature that we found, which was interesting, was the more hyperreflective foci was also associated with more frequent treatment injections. So from physiology and pathology uh, uh, reports, we know that fibrin is a frequent feature in these histopathologic membranes. So we hypothesize that these high frequency injection requiring lesions are very highly leaky. And with that leakage comes high molecular weight proteins such as fibrin. And when fibrin is deposited, it creates another lamina upon which more neovascularization can grow. And with this highly leaky membrane, there's more scaffold and more CNV layers. So what we were seeing was a feature, histopathologic feature perhaps of these highly leaky membranes, and which explained why we required frequent injections in these eyes. And to sort of have a sanity check, here's an example of these three-dimensional lesions rendered in 3D to show you how complex these lesions are. So they start with maybe a feeder vessel that penetrates the Brooks membrane, and then you could see how they grow like vines on the tree with multi-layered complexity. And so in summary, lesions that are complex in 3D require high frequency injections. So it would be nice if we had a more feasible and less complex parameter, but this time we find that this is a very indicative feature. The other question we had is, what is the relationship between these complex lesions and the surrounding choriocapillaris? And the possibility of choriocapillaris ischemia as sort of the inciting and the nidus for growing CNV is something that's been proposed by Jerry Luddy for a long time. So in this conceptualization, you have a normal choriocapillaris with a healthy RPE sustaining the normal choriocapillaris. And then as we age, there's a loss of the choriocapillaris, and with it, perhaps RPE ischemia. Once the RPE becomes ischemic because of the unhealthy choriocapillaris, then it starts to secrete these angiogenic factors. And angiogenic factors then invite the neovascular membranes to grow as a reactive process to the RPE and choriocapillaris ischemia. So these CNVs as a reactive regenerative process perhaps has been proposed for a long time by Jerry Luddy. So in that concept then, the aging choriocapillaris could be partially compensated until it reaches a certain point where it's super ischemic, like a desert. And then at some point, then the RPE becomes stimulated to secrete angiogenic factors and grow an oasis of neovascularization. And if that ischemic RPE is actively secreting, maybe this CNV would grow into a more complex three-dimensional structure. So that was our hypothesis. So to do that, we first needed to analyze the choriocapillaris objectively. And as you can see, there's a lot of artifacts in the choriocapillaris related to the CNV itself and to the RPE thickening. So we had to compensate for these artifacts. And this is a technique proposed by Wang and Rosenfeld. And so you take the structural OCT and you reverse it, multiply it by the OCT angiography, and that compensates for the signal attenuation. Once you have this compensated choriocapillaris, we then adjust it for the signal strength, binarize it, remove the artifacts from the superficial capillaries, and to remove artifactual small flow voids. That creates a map of the choriocapillaris, and we also remove the actual CNV because it is not really related to the choriocapillaris. And from there, we extract quantitative features, flow deficit density, number, and mean flow deficit size. And then we look at the CNV in a cross-sectional OCT. And as I already told you about these features, flow signal height, number of flow layers, and thickness of the flow signal. And we look for correlations between those two things. So the choriocapillaris surrounding the CNV and the CNV complexity. And we analyzed the choriocapillaris in three main areas in the whole en face scan outside the CNV. also in an annulus to explore this feature of sort of a peri-lesion halo, and in the area outside the annulus, outside the CNV. And so here we had 29 eyes of patients that were being treated, and we did not find any correlation with age or scan quality as a sanity check. And then we had a sort of a variety of number of layers in these CNVs. So when we look at examples of these CNVs and surrounding choriocapillaries, and here we apply two thresholds, again, for validation of our findings. So if you look at a single layer CNV, you see the number of flow deficits. And then with a double layer CNV, we're starting to see more flow deficits, bigger flow deficits. And then triple layer CNV, we see even more. When we looked at these correlations, we found that the highest CNV flow was the most reliable and consistent variable. And as the CNV flow increases from left to right, you see that the density of flow deficit increases. And again, the flow deficit count goes down, which to us means that the number of flow deficits is decreasing as the CNV grows higher. And then the flow deficit size increases. So the number increases, the number decreases, but the size increases, which suggests that they're perhaps coming together and coalescing into larger and larger lesions as the CNV grows thicker. So overall, we found that 3D complexity significantly correlates with choriocapillaris ischemia and flow deficits. And so as the height of the CNV increases, the flow deficit count goes down, but the density and size go up, suggesting that they're coalescing into larger and larger ischemic areas. And the flow signal height was the most correlated with FD parameters. So perhaps to put it all together, this is a vicious cycle where choriocapillaris ischemia is inviting these multi-layered CNVs that keep growing and leaking. And with RPE ischemia, that process then becomes harder to control, requiring more frequent anti-VEGF injections. And with that, I'd like to thank you for your attention. And I thank all the students, especially Peter, who's here today, and Janice, who collaborated on this project, as well as Brian, who's now at Stanford as a resident. And I thank you for your attention. I'll be open to take questions next.